Something broke last week. Not a machine, not a pipeline, not a satellite. The planet itself crossed a line that hadn't been crossed in 140 years, and the way it happened defies almost everything we think we understand about how weather is supposed to work. Moscow woke up buried. 21 centimeters of snow fell on the Russian capital in what felt like a single breath, and when meteorologists pulled out their records and started flipping back through the pages, they had to go all the way back to 1880 before they found a comparable moment. That is not a small thing. That is a record that survived 2 world wars, the invention of the automobile, the entire space age, the digital revolution, and every climate anomaly the 20th century could throw at it. And then, quietly, in a matter of hours, it was gone. But here is where the story stops being just about snow. Because while Moscow was disappearing under a white blanket, the oceans on the other side of the planet were doing something almost exactly opposite. Sea surface temperatures in parts of the Atlantic and Pacific were running so far above normal that researchers kept double-checking their instruments. The planet was simultaneously producing record cold in one location and record heat in another, and the mechanism connecting both of those extremes is the same invisible structure of moving air that most people never think about at all. To understand what is actually happening, you have to go up, way up. Not to space, not quite, but to the edge of where weather lives, where the atmosphere thins out and the winds that circle the Earth at jet stream altitudes begin to behave like something almost alive. The atmosphere is not a static blanket sitting over the planet. It is a constantly churning, rotating, stratified system of pressure zones and temperature gradients that move energy from the equator toward the poles in a continuous loop. That circulation is what we call climate, and it has been running, with variations, for billions of years. But the variations matter enormously, and right now the variation we are living through is one of the most dramatic in modern recorded history. Start with the ocean, because that is where the energy comes from. El Niño is a periodic warming of the central and eastern tropical Pacific Ocean, and it has been roaring since mid-2023 in a way that has surprised even veteran climatologists. When that patch of ocean heats up, it does not stay local. It pumps enormous quantities of heat and moisture into the atmosphere above it, and that energy radiates outward like a disturbance in a pond. The ripples travel thousands of miles. Ocean heat does not just evaporate, it restructures the atmosphere. Warmer ocean surfaces mean warmer air above them, and warmer air changes the pressure gradients that drive the global wind circulation. When you alter pressure gradients at the surface, you alter the behavior of the jet streams high above, and when the jet streams change their behavior, everything downstream changes with them. Think of the jet stream as a river of air flowing around the planet at altitudes where commercial aircraft cruise. Under normal conditions, that river moves in a relatively tight, fast westerly band across the mid-latitudes. It acts as a barrier, a wall of wind that keeps polar air locked in the Arctic where it belongs and keeps milder Atlantic air circulating across Europe and Western Asia. But that river is not always straight. Sometimes it meanders, sometimes it bends into enormous loops that dip far south or bulge far north, and when it does, the consequences on the ground are severe. What happened over the North Atlantic in the days leading up to Moscow's record snowfall was the formation of what meteorologists call a blocking pattern. A blocking pattern is essentially a traffic jam in the atmosphere. A dome of high pressure established itself over the North Atlantic and refused to move. High-pressure systems rotate clockwise in the northern hemisphere, and this one acted like a wall thrown up across the normal flow of westerly winds. The jet stream, which normally would carry mild air eastward across Europe and into Russia, could not get through. It was forced to detour. When the jet stream is blocked and redirected, it often forms what is called an omega block, named for the shape the wind pattern takes when viewed from above. The warm air bulges northward on either side of the block while a deep trough of cold air is dragged southward through the centre. In this case, that trough opened directly over western Russia, and pouring down through that trough like water through an open drain came air from the Arctic. Arctic air is not simply cold, it is a different category of cold. It is air that has been sitting over the polar ice cap for weeks or months, radiating heat upward into the void of space, getting denser and colder with every passing day. When a pathway opens for that air to surge southward, it does not drift. It plunges, and it carries with it the capacity to produce weather events that feel impossible given the season, given the global temperature trends, given everything the headlines have been telling us about a warming planet. Moscow received 21 centimetres of snow. To put that in context, the previous record for this time of year was set when the telegraph was still a new technology, when electric light was still experimental, when the first commercial telephone exchange was barely open. The people who measured that snowfall in 1880 were using instruments that had nothing in common with modern meteorological satellites, and yet their record stood for a century and 4 decades, until now. The question worth sitting with is not just how this happened. The more unsettling question is why our warming world is producing events like this at all. Because on the surface, there seems to be a contradiction. If the planet is warming, why is Moscow setting cold records? If ocean temperatures are at historic highs, why is there record snow falling in Russia? The answer to that apparent paradox is one of the most important and counterintuitive insights in modern climate science. The Arctic is warming faster than anywhere else on Earth. This is not a projection or a model output. It is a measured, documented reality. The region around the North Pole is heating up at roughly 4 times the global average rate. The sea ice that once covered vast stretches of the Arctic Ocean year-round is retreating. The temperature difference between the Arctic and the mid-latitudes is shrinking, and that temperature difference is not just a number, it is the engine that drives the polar jet stream. The jet stream is powered by the contrast between cold polar air and warmer mid-latitude air. The greater the contrast, the stronger and more stable the jet stream. When that contrast weakens, the jet stream weakens with it. A weaker jet stream is more prone to meandering, more prone to forming the large, slow-moving loops and blocking patterns that drag Arctic air into unusual places and hold it there for extended periods. In other words, a warming Arctic does not simply make winters milder everywhere. It makes them more volatile. It makes them more prone to extremes. A warming Arctic can paradoxically deliver colder temperatures to places like Moscow, London, or the eastern United States, not because the world is getting colder, but because the atmospheric machinery that normally keeps cold air contained is losing its stability. The walls are getting weaker, and when the walls weaken, things spill out. This is the kind of climate behaviour that is extraordinarily difficult to communicate, because it sounds backwards. It sounds like the kind of thing someone says when they want to deny that warming is happening. But the science is clear, and it has been building for decades. A warmer Arctic is not just a far-off ecological tragedy about polar bears and shrinking ice. It is a direct mechanical influence on the weather that billions of people experience every single day. The jet stream is being rewired, and the rewiring produces both the record snowfall in Moscow and the record ocean heat in the tropics. They are not contradictions. They are the same story told from 2 different latitudes. Now step back even further, because the Moscow snowfall and the Atlantic blocking pattern are happening inside a much larger and more extraordinary context. The past several years have produced a string of global temperature records that have genuinely alarmed the scientific community. Not because any individual record is so surprising, but because of how many records are being broken, how fast, and how the records themselves seem to be accelerating away from what the models predicted. The year 2023 was the hottest year ever measured on Earth by an enormous margin. Every month from June through December of that year set a monthly temperature record for the planet. The ocean heat content reached levels that broke the instruments of our previous understanding. Coral reefs around the world experienced bleaching events of unprecedented scale. Antarctic sea ice hit record low extents, not by small margins but by margins that left researchers struggling to find explanations. And then 2024 arrived and immediately began competing. The first few months of the year continued setting records. Ocean temperatures in the North Atlantic reached levels that had never been seen before in the instrumental record, which itself goes back to the mid-19th century. Scientists who had spent careers studying ocean dynamics were publicly expressing surprise, not because the direction of change was unexpected, but because the magnitude and the speed were exceeding projections. El Niño is part of the explanation. El Niño events have always driven global temperature spikes. The strong event of the mid-1990s, the even stronger one in 2015 to 2016, both produced global temperature records at the time. This current event is occurring on top of a baseline that is already dramatically elevated by decades of accumulated greenhouse gas warming, which means it is amplifying an already amplified signal. The result is a global temperature curve that is spiking upward at a rate that, when plotted on a graph, looks almost vertical. But here is where researchers are genuinely puzzled. Even accounting for El Niño, Even accounting for the steady long-term warming trend from carbon dioxide and methane and other greenhouse gases, the temperatures of the past 2 years are running hotter than the models predicted. There is an excess. Scientists call it an anomaly within the anomaly. And the search for explanations has produced some genuinely fascinating and sobering hypotheses. One of the most discussed is the eruption of an undersea volcano in the South Pacific in early 2022. The explosion was one of the most powerful ever recorded by modern instruments, and it was unusual in a critical way. Unlike most large volcanic eruptions, which inject sulfur dioxide into the stratosphere and temporarily cool the planet by blocking sunlight, this eruption injected an enormous quantity of water vapor into the stratosphere instead. Water vapor is itself a greenhouse gas. At stratospheric altitudes, it can persist for years. Some researchers believe this stratospheric water vapor injection contributed measurably to the anomalous warming seen in 2023 and 2024. Another hypothesis involves a reduction in shipping emissions. For decades, large ocean-going cargo ships burned dirty, sulfur-heavy fuel that released sulfur dioxide particles into the atmosphere over the ocean. Those particles acted as the seeds for low marine clouds, and those clouds reflected sunlight back into space, effectively providing a global cooling effect that was masking some portion of the underlying greenhouse warming. When international regulations forced a dramatic reduction in sulfur emissions from ships starting in 2020, that inadvertent sunscreen over the oceans began to disappear. The result, some researchers argue, is that ocean surfaces that had been slightly shielded from full solar forcing are now absorbing more heat than they did before. A kind of unintentional geoengineering experiment ended, and the ocean began catching up to the full force of a warming atmosphere. Neither of these explanations is definitive on its own, and both are still actively being debated and researched. But they illustrate something important about where climate science finds itself right now. The basic physics of greenhouse warming is settled and has been for a very long time. Carbon dioxide traps heat. More carbon dioxide means more heat. The planet is warming. None of that is in question. What is genuinely uncertain, and what makes this moment scientifically extraordinary, is the question of how many feedback loops and secondary effects are interacting with the primary warming signal, and how quickly those interactions are shifting the system into new territory. The atmosphere is not a simple machine with one dial and one output. It is a system of almost incomprehensible complexity, where changes in ocean temperature affect atmospheric circulation, which affects ice coverage, which affects how much sunlight the planet absorbs, which affects ocean temperature again. Every feedback influences every other feedback, and right now several of those feedbacks appear to be accelerating simultaneously. The blocking pattern that buried Moscow in snow is one symptom. The boiling ocean temperatures beneath El Niño's influence are another. The shrinking Arctic ice is another. The disrupted jet stream is another. They are all expressions of the same underlying shift in the planetary energy system, and they are arriving together, overlapping, compounding. What does this mean for the future? The honest answer is that the uncertainty itself is the story. Climate scientists are not uncertain about the direction of change. The planet will continue warming as long as greenhouse gas concentrations continue rising. That trajectory is clear. What is less clear is the texture of that warming. How lumpy will it be? How extreme will the individual events be? How often will blocking patterns form over the North Atlantic? How frequently will the Arctic plunge cold air into places like Moscow, or the American Midwest or Central Asia? How often will ocean temperature records fall? The records of 1880 were set in a world with no satellites, no computers, no global communications network. The people who made those measurements could not have imagined that their careful documentation of a snowfall in Moscow would still matter 140 years later. They could not have imagined that their record would become a data point in a global scientific effort to understand a planetary transformation of this scale. And yet here we are, in the era of satellites and supercomputers and global sensor networks that cover the entire surface of the Earth, and we are still being surprised. The system is moving in ways that our best models are struggling to keep up with. That is not a failure of science. Science does not fail by being surprised. Science advances precisely because reality pushes back against expectation and forces deeper investigation. But it is a signal, a clear, unmistakable signal that the pace of change is faster than expected, that the interactions between components of the climate system are more complex than our models fully capture, and that the Earth we are living on is in the middle of a transition whose endpoints we cannot yet see clearly. The snow that fell on Moscow in those hours was not an isolated event. It was a message. Not a poetic message, not a metaphor, but a literal physical signal embedded in the behavior of a planetary atmosphere that is reorganizing itself under the pressure of forces that have been building for generations. The blocking pattern that caused it, the weakened jet stream that allowed it, the warming Arctic that destabilized the jet stream, the elevated ocean temperatures that energized the entire system, all of these are connected. All of these are chapters in the same document. 1880 was the year the world still thought it could consume its way into prosperity without consequence. The record that was set that year in Moscow carried forward through everything the 20th century could throw at it, surviving as a quiet piece of data in a meteorological archive that almost no one thought about. And then the planet decided to speak, and it chose a language that goes back 140 years to make itself understood. We are listening now. The question is whether we are listening fast enough. Part 1 of 2. There is a particular moment in the study of climate systems where the conversation shifts from what is happening to how we know what is happening. And that shift matters, because the credibility of every claim I just made rests entirely on the infrastructure of measurement that makes those claims knowable in the first place. The meteorologists who recorded that snowfall in Moscow in 1880 were working with instruments that were mechanical and local. A thermometer measures the air around it. A rain gauge collects what falls directly into its opening. If you wanted to know what the weather was in Russia in the 19th century, you relied on human observers stationed at specific points, recording their observations by hand, trusting their competence and their honesty, and then waiting for those records to be transmitted by post or telegraph to central archives where they could be compiled. The entire system was slow, granular, and fundamentally limited by geography. Most of the Earth had no observers at all. The oceans were almost entirely blind. The upper atmosphere was completely invisible. Now, fast forward 140 years, the satellite that launched into orbit in 2015 and has been operating ever since has single-handedly collected more temperature data from the atmosphere than existed in written form for all of recorded history up until that point. And that is just one satellite. There are dozens. The network of buoys floating in the oceans, each one automatically transmitting data about water temperature, salinity, and pressure back to shore multiple times per day, collectively covers millions of square kilometers of open water that were pure guesswork a generation ago. The weather stations on land have gone from manual observation to automated sensor arrays that measure and transmit continuously. We have weather radar that can peer inside clouds and see where precipitation is forming. We have infrared sensors that can measure the temperature of ocean surfaces from space with an accuracy of a fraction of a degree. The data infrastructure we have built to observe the Earth is, quite literally, something that would have seemed like science fiction to the meteorologists of the 1880s. And it is this infrastructure, this intricate global tapestry of sensors and satellites and automated stations, that allows us to do something that previous generations could never do. We can detect when something has changed, not just locally, but globally. We can compare this year to last year, to a decade ago, to a century ago. We can establish baselines and measure deviations from those baselines with precision. And what that precision has revealed is something that deserves to sit with you for a moment. The planet is not warming in a smooth, steady, predictable way. It is warming in a way that is lumpy and irregular, filled with regional anomalies and temporal spikes that make the underlying trend harder to see, but far more consequential. The global average temperature is rising, yes, that is the headline, but the headline is masking something more complex happening underneath. Consider the North Atlantic, which I mentioned briefly before, but which deserves deeper attention because it is a region that is reshaping itself with particular intensity right now. The North Atlantic is not warming evenly. There are parts of it that are warming rapidly, other parts that are warming more slowly, and some regions where the warming appears to be driven by mechanisms that are only partially understood, even by the researchers who study ocean dynamics for a living. Between 2023 and the middle of 2024, a region of the North Atlantic experienced temperature anomalies that were so far above historical patterns that they triggered an entire new category of scientific concern. The Atlantic meridional overturning circulation is what oceanographers call the conveyor belt of the Atlantic Ocean. It is a system of currents that carries warm water northward from the tropics, cooling as it goes, and then sinking in the far north and returning southward as a deep cold current. This circulation has been running for thousands of years, moving heat around the planet, moderating climates on both sides of the Atlantic, making Western Europe far warmer than it has any right to be given its latitude. Dublin and London and coastal Norway should be locked in ice for half the year if you look at a globe and compare their latitude to locations in North America. But they are not, because the Atlantic circulation is pumping warm water northward. That circulation has some slack in it, some tolerance for variation, but that slack is not infinite. What researchers noticed in the data from 2023 and into 2024 was that certain subsurface water masses in the Atlantic were warming in ways that were difficult to explain through surface heating alone. The water at depth was getting hotter, which meant something was transporting heat downward that had not been doing so as intensely before. Some of the explanations circulating through the research community are genuinely alarming, because they hinge on the possibility that the circulation itself is beginning to slow. A slowing circulation would mean less heat transported northward. It would mean Western Europe would gradually become colder relative to its current climate. It would also mean that the heat not being transported north was staying in the tropics and the subtropics, intensifying warming there. You would get a geographic redistribution of temperature, which sounds abstract until you realize that it maps onto disrupting agricultural zones, shifting where water is available, reshaping where human populations can comfortably live. Now, the Atlantic circulation has slowed before. It has not shut down completely, not in human history at least, but there is evidence from ice cores and sediment layers and other paleoclimate records that it has undergone significant reductions in the past. When it has, the consequences have been dramatic. The Younger Dryas, a period of rapid cooling that occurred roughly 12,000 years ago, is believed to have been triggered by a disruption to the Atlantic circulation caused by a massive influx of fresh water from melting glaciers. If that happened then, could it happen now? There is fresh water currently entering the North Atlantic at unprecedented rates. The Greenland ice sheet is melting faster than it has at any point in the instrumental record. Meltwater is pouring into the northern Atlantic. Some of this water is coming from glaciers that discharge directly into the ocean. Some is coming from rivers that drain the interior of Greenland. The cumulative effect is that the surface salinity of the North Atlantic is dropping in certain regions, which makes the water less dense, which makes it sink less readily, which could, in theory, slow the circulation down. But here is where things get genuinely complicated. The observations we have are not yet conclusive about whether the circulation is actually slowing, or whether what we are seeing is normal variability with an unusual warming signal riding on top of it. The Atlantic circulation has natural cycles. It speeds up and slows down on decadal timescales. What is difficult to disentangle is how much of the current anomaly is part of that natural cycle, and how much is a response to the forcing that we are applying to the climate system. The research is ongoing. The concern is real. The timeline is unclear. But the possibility that one of the planet's great thermostat systems could be shifting is not a fringe hypothesis anymore. It is being actively investigated by serious oceanographers because the data is suggesting something unusual is happening. And this is where the conversation needs to expand beyond just the Atlantic. Because what is striking about the global temperature records of the past 2 years is not just that they are high, but where they are high and where they are surprisingly not that high. The Arctic is warming faster than anywhere else, yes, but the North Atlantic specifically is warming even faster than the Arctic as a whole. The tropical Pacific has warmed, but the Atlantic warming is outpacing it, and meanwhile certain other regions are warming more slowly than the global average, which means something in the system is concentrating heat in specific locations. That concentration suggests that the normal redistribution machinery is being disrupted or redirected. The ocean is not a passive recipient of atmospheric warming. It is active. It has its own circulation patterns that move heat around. It has stratification layers that prevent mixing. It has chemical reactions that are altered by temperature. It is a profoundly complex system, and when you push on it hard enough, it pushes back in ways that can be counterintuitive. A region can warm dramatically, while the global average rises more slowly. A region can warm while another nearby region stays relatively stable. The global signal is the sum of all these regional variations, and right now those regional variations are expressing themselves in ways that our models are having trouble predicting. This is the moment where a lot of climate communication breaks down, because the public narrative around global warming is often boiled down to a single number. The planet is warming by X degrees, everything is getting hotter everywhere, but the reality is far more textured than that. Warming is not uniform. Some regions warm faster, some processes amplify the warming, some create regional cooling effects. The net effect is warming, but the path to that warming and the consequences along the way are wildly varied and location-specific, which brings us back to the jet stream and the blocking patterns and the snow in Moscow, because these phenomena are not contradictions to the warming narrative. They are weather expressions of the warming narrative. When the Arctic warms faster than the mid-latitudes, you weaken the temperature gradient that drives the jet stream. A weakened jet stream is more prone to meandering, and meandering jet streams bring unusual weather to unusual places. That weather might be cold and snowy, or it might be hot and dry depending on which side of the meander you live on. Both are expressions of the same underlying disruption. Both are consequences of a warming planet, not proof against it. The Moscow snow, the Atlantic heat, the slowing circulation, the vanishing Arctic ice, the bleaching reefs, the failing crops in certain regions and the record harvests in others. These are all variations on a theme. They are all what happens when you add enough energy to a complex system to push it away from its historical baseline and into new territory. The system does not warm smoothly. It responds, it adapts, it compensates, and those compensations create cascading effects throughout the rest of the system. What is particularly difficult about the moment we are in right now is that we are not just observing this transition. We are living through the exact period when the disruptions are becoming large enough to be undeniable, but not yet so large that the old systems have fully broken and new equilibrium has established itself. We are in the transition. And transitions are by definition unstable. They are characterized by variability and surprise. They are characterized by the kinds of records we are seeing. The reason the records are falling so fast is not because we are adding heat slowly and steadily. It is because we are pushing a complex system past certain thresholds, and once a threshold is crossed, the system tends to accelerate. Consider the ice-albedo feedback, which is one of the most important and least commonly discussed acceleration mechanisms in the climate system. Ice is white. It reflects sunlight back into space. The dark ocean underneath it is dark because it absorbs sunlight. As Arctic ice melts, you replace reflective surface with absorptive surface. That means more of the sun's energy is absorbed, that warming drives more melting, that melting exposes more dark surface, and so on. It is a feedback loop that amplifies the initial warming signal. For decades, this feedback was present but relatively modest, because the amount of ice melting was still relatively small, but we are reaching a regime where the feedback is becoming significant, where the ice loss is getting large enough that the amplification is becoming a first-order effect in the regional warming. The same principle applies to other components of the system. As permafrost thaws, it releases methane and CO2 that have been locked away for thousands of years. These gases drive more warming, which thaws more permafrost, which releases more gas. Another feedback loop. As the forest systems in the tropics warm beyond certain thresholds, they become more prone to drought and more vulnerable to fires. Fires release the carbon stored in those forests as additional CO2. More CO2 drives more warming. More warming makes forests drier. Another loop. What researchers have come to understand is that the climate system is filled with these feedback loops, and for a very long time, they were all operating somewhat independently, each one with its own timescale and its own magnitude. But we are now pushing hard enough on the overall system that multiple feedbacks are becoming active simultaneously. The ice-albedo feedback is accelerating. The permafrost feedback is starting to kick in measurably. The forest feedback is showing signs of activation. The ocean heat uptake is changing the salinity, which is affecting the circulation. All of these at once, on top of the baseline warming from greenhouse gases. This is what acceleration looks like. And this is why the records are not just high. They are accelerating. The rate of change is increasing. The gap between the hottest years on record is shrinking. The anomalies are getting larger. The system is not approaching a new equilibrium gradually. It's being pushed hard enough that it is beginning to reorganize itself on timescales that are compressed by geologic standards, but still measurable on human timescales. This is the difference between a car gradually speeding up on a highway and a car that is beginning to accelerate downhill. The system has enough momentum and enough feedback mechanisms that once you push it hard enough, it does not just warm at the same rate you are adding energy. It begins to warm faster than the forcing alone would predict. This is what the models have been predicting, theoretically, for decades. It is what the basic physics said should happen. But there is a difference between a mathematical projection in a climate model and seeing that projection show up in real data. When you see it in the real data, when you watch the records fall and the anomalies get larger, and the patterns shift in the directions that the models predicted they would shift, that is when the abstract becomes concrete. That is when you understand that you're not reading about a future possibility, you are watching it arrive. Part 1 of 2 ends here. Continue to Part 2 for the remaining approximately 50 minutes of content. Part 2 of 2, now. One of the complications in communicating about climate change is that most people, even people who intellectually understand that warming is happening, still harbour the assumption that it is a gradual process. They imagine a slow creep toward higher temperatures, with consequences arriving on timescales measured in decades. The idea of acceleration, of nonlinear change, of feedback loops that can suddenly amplify the signal is harder to hold in mind. But it is crucial to hold it, because acceleration is not an exotic outcome. It is what you get when you push a complex system past certain thresholds, and we are increasingly certain that we have crossed some of those thresholds already. The other complexity is that the consequences of climate change are not all negative in every location at every time, which is not to say that they are positive on balance, they are decidedly not. But on the local and regional level, in the short term, you're going to see winners and losers. Parts of Canada and Russia are going to have longer growing seasons. Certain agricultural regions are going to see improved conditions for a time. Some regions that were marginal for certain crops will become viable. This sounds almost neutral when you say it in the abstract, but when you place it in the real world of human migration and economic disruption and geopolitical tension, it becomes far more consequential. There is a reason that geopolitical strategists are beginning to pay attention to climate change. It is not primarily because of existential risk from some far future scenario. It is because of the near-term economic and social disruptions that come from rapidly shifting climate zones. The agricultural regions that feed the world are not uniformly distributed. The major grain-producing regions in the Midwest of North America and in Eastern Europe, and in parts of Asia, feed billions of people. If the climate patterns that have made those regions productive shift, the consequences propagate globally. It is not just about the temperature in one place going up. It is about the implications of that temperature change for water availability, for crop viability, for where people can live and work and sustain themselves. The monsoon systems that bring water to South Asia have already begun showing signs of disruption. The patterns are not what they used to be. Some years the rains come late, some years they are heavier than historical patterns, some years they shift geographically. These are changes that would seem modest on a global climate graph, but translate into real crop failures and real disruptions to agricultural systems that hundreds of millions of people depend on. When you start connecting climate changes to food security, to water stress, to human migration, you're suddenly talking about consequences that are not hypothetical or far future. They are here now, and they are beginning to reshape where and how people live. This is where climate change stops being a pure science story and becomes a story about human institutions and their capacity to adapt. The climate is going to keep changing. That is locked in. Even if we stopped emitting greenhouse gases today, the warming that has already been built into the system would continue for centuries. The inertia of the climate system is enormous. The oceans have tremendous heat capacity. It takes a long time for them to warm up, but it also takes a long time for them to cool down. We have committed ourselves to decades of continued warming beyond what we are already experiencing, simply because of the lag between when emissions occur and when the full warming effect manifests in the atmosphere and oceans. Given that, the question becomes not whether the climate will change, but how we manage the consequences. How do we shift agricultural systems in anticipation of changing rainfall patterns? How do we move water to regions where it is becoming scarce? How do we modify infrastructure that was built for a climate that no longer exists? How do we help populations migrate and resettle when the regions they have inhabited for generations become hostile to human habitation? These are questions that require coordination, foresight, and resources on a scale that humanity has rarely attempted, and they are becoming urgent. But there's another layer to this conversation that is worth surfacing, because it is the part that most climate communication sidesteps or handles obliquely. The climate is not just changing in response to greenhouse gases, It is changing in response to human activity more broadly. The satellite data I mentioned earlier, the observational infrastructure that lets us see what is happening to the planet, has revealed something that was almost invisible before. Human civilization has become an active geological force. We are not just changing the climate, we are changing everything. Look at the nitrogen cycle. For millions of years before industrial agriculture, the amount of nitrogen fixed by biological processes and converted into forms that plants could use was relatively stable. The nitrogen cycle was in balance. Then we invented the Haber-Bosch process, a chemical technique that allows us to synthesize ammonia from atmospheric nitrogen at industrial scale. We did this in order to produce fertilizers, because fertilizers let us grow more food using less land. The Haber-Bosch process is arguably one of the most important innovations in human history, because it enabled the Green Revolution and the massive increase in global food production that allowed the population to expand from about 2 billion people in 1930 to nearly 8 billion today. But there is a cost. We are now fixing more nitrogen each year through the Haber-Bosch process than all biological nitrogen fixation processes combined. We are running the nitrogen cycle at roughly double its pre-industrial rate. That excess nitrogen runs off into rivers and eventually into coastal oceans, where it fertilizes algae blooms. Those blooms consume oxygen and create dead zones. The dead zones are expanding, they are destroying fisheries, they are collapsing local ecosystems, and this is not a climate change problem specifically. It is a planetary boundary problem. We have exceeded the safe operating space for nitrogen cycling. The same is true for phosphorus. Phosphorus is the limiting nutrient for biological productivity in most of the world's oceans. For millions of years, the amount of phosphorus in bioavailable forms was relatively limited. Then we began mining phosphorus from geological deposits and spreading it on agricultural land. We are now moving phosphorus through the food system at rates that are completely unprecedented. Some of it washes into rivers and oceans, some accumulates in soils, some ends up in landfills and municipal waste. We have disrupted the phosphorus cycle as thoroughly as we have disrupted the nitrogen cycle. Look at the carbon cycle. For hundreds of thousands of years before the Industrial Revolution, the carbon cycle was in balance. Carbon moved between the atmosphere, the oceans, the soil, and living organisms in patterns that had been relatively stable. The concentration of carbon dioxide in the atmosphere varied between about 180 and 300 parts per million in response to natural cycles. Then we started burning fossil fuels. We extracted carbon from geological storage, converted it to CO2, and released it into the atmosphere. We are now at over 420 parts per million. That is a level that has not existed in millions of years. The carbon cycle has been pushed radically out of balance, and it will stay that way for centuries even after we stop emitting carbon dioxide. Look at the sulfur cycle, and the metal cycling and the plastic debris that is now distributed throughout the oceans, in amounts that are measurable and increasing. Look at the way we have restructured river systems with dams and diversions, so that many of the world's largest rivers no longer reach the ocean in their natural form. Look at the way we have altered terrestrial vegetation patterns through agriculture and urbanization, so that the surface properties of the land have changed. Look at the way we have changed the composition of the atmosphere so fundamentally that it has altered its optical properties. Every major biogeochemical cycle on the planet is now dominated by human activity. This is the observation that leads some researchers to propose that we have entered a new geological epoch, one that should be called the Anthropocene. The Holocene, the previous epoch, began roughly 11,700 years ago and was characterized by climatic stability and predictability. That period, that epoch, is over. We have pushed the planet out of the Holocene and into a new state. Everything that human civilization built was built under the assumption that the Holocene conditions would persist. Stable climate, predictable seasons, agricultural productivity that varied within certain bounds. We built our entire infrastructure and our entire institutions on that assumption. Now we are in the Anthropocene, and the rules have changed. The climate is no longer stable. The seasons are no longer predictable in the way they used to be. The agricultural zones are shifting. The water cycles are being disrupted. The ecosystems are reorganizing. And all of this is happening faster than institutions can typically adapt. This is not a failure of individual scientists or policymakers or engineers. This is a structural problem of time mismatch. We have a system, human civilization, that operates on timescales measured in years and decades. We are pushing on a planetary system that operates on timescales measured in centuries and millennia. The feedback between those two timescales is creating a situation where we are changing the planet faster than we can understand the full implications of those changes. The feedback loops I mentioned earlier, the ones that are beginning to accelerate, are themselves expressions of this time mismatch. The permafrost that is thawing has been frozen for thousands of years. It contains the accumulated carbon of millennia. When it thaws, that carbon is released on human timescales, not geological ones. The forests that are beginning to show signs of stress have developed over thousands of years under relatively stable climate conditions. When those conditions shift, the forests do not smoothly transition to a new state. They often collapse, sometimes over the course of a single decade. The ice sheets that are melting have persisted since before human civilization existed. When they begin to collapse, the sea level does not rise gradually and predictably. It rises in pulses. This is the physics of nonlinear systems. When you push a system that has been stable for a very long time out of equilibrium, the response is not proportional to the pushing force. The response is often delayed, and then it accelerates, and then it overshoots, and the system oscillates around a new equilibrium before finally settling. We are in the delayed response phase right now, transitioning into the acceleration phase. What that transition looks like depends enormously on how much further we push the system. The Paris Agreement, signed in 2015, committed the world to limiting warming to 1.5 degrees Celsius above pre-industrial levels, or 2 degrees if that was not achievable. The idea behind the numbers was that staying below those thresholds might allow us to avoid the most severe consequences. But we have to be honest about where we stand. The world has already warmed by roughly 1.2 degrees above pre-industrial levels as of 2024. Given the emissions that are already locked into the system, given the current trajectory of global emissions, given the feedback loops that are beginning to activate, we are very unlikely to avoid exceeding 1.5 degrees. We are likely to exceed 2 degrees. We might, depending on choices made in the next 5 to 10 years, end up heading toward 2.5 or 3 degrees or higher by the end of the century. Now, when scientists talk about the difference between 1.5 and 2 degrees, it might sound small. It is 1 degree. But in the context of planetary systems, 1 degree represents a massive amount of additional energy in the system. It represents the threshold where certain ecosystems cross from stressed to collapsing. It represents the point where certain regional climates become fundamentally hostile to agriculture. It represents the difference between a disruption and a catastrophe for many regions of the world. And at higher levels of warming, the differences compound. The gap between 2 degrees and 2.5 degrees is the difference between severely disrupted and fundamentally transformed. But here is where the conversation becomes genuinely difficult, because we are not moving toward a single outcome. We are moving toward a range of outcomes, and which outcome we experience depends on choices that have not been made yet. The physics dictates that if we continue emitting greenhouse gases at current rates, we are heading towards significant warming. That is not a choice point, that is locked in. But the magnitude of the warming over the next 50 years depends on whether we accelerate emissions further, stabilize them, or begin reducing them. It depends on whether the feedback loops accelerate or whether we manage to keep them from accelerating. It depends on choices that are made at the intersection of technology, policy, economics, and politics. And this is where most of the climate discussion breaks down, because it stops being pure science at this point and becomes a story about human agency and human choices. The physics says what can happen. Human choices determine what actually happens, and human choices are made in contexts of enormous complexity and competing interests and uncertainty about consequences. Consider the energy system. For roughly 200 years, human civilization has been powered primarily by burning fossil fuels. We built the entire modern world on the back of cheap, abundant, energy-dense hydrocarbon fuels. Every system we have built, from transportation to electricity generation, to heating to industrial processes, was designed around the assumption that those fuels would be available and cheap indefinitely. Now abruptly, on a historical timescale, we need to transition away from those fuels. We need to do it rapidly. We need to do it while simultaneously maintaining the energy supply that billions of people depend on. This is technologically feasible. The renewable energy technologies exist. Solar panels are incredibly efficient and getting more so. Wind turbines work. Hydroelectric power works. Battery technology is improving. In principle, we could transition the entire global energy system to renewables within a few decades. But that is in principle. In practice, it is extraordinarily complex. Renewable energy is variable. The sun does not shine at night. The wind does not blow constantly. That variability requires either massive energy storage systems or a completely redesigned grid or both. Energy storage at the scale required does not exist yet. Grid redesign is extraordinarily complex, and all of this needs to happen while maintaining the energy supply to industries and cities and hospitals and data centers that depend on it. There is also the question of what we do with the existing fossil fuel infrastructure. We have invested trillions of dollars in coal mines, oil refineries, natural gas pipelines, power plants, and supply chains that are designed around fossil fuels. Those investments did not get made yesterday. They are the accumulated infrastructure of the global economy. Transitioning away from that infrastructure rapidly means writing off those investments. That is economically disruptive. It is politically difficult. It creates winners and losers. In some regions, entire economies are built around fossil fuel extraction or fossil fuel-dependent industries. Transitioning away from them means disrupting those economies. That creates political resistance, which is to say that the reason we have not solved the climate change problem is not because we do not know how to solve it. It is because solving it requires disrupting the existing energy system, which requires powerful actors to voluntarily give up the power and profit they derive from that system. And powerful actors rarely do that voluntarily. They do it only when they are forced to by regulation, or by economic pressure, or by political will strong enough to overcome the countervailing forces. This is starting to happen in some places. Europe has committed to climate neutrality by 2050 and has actually implemented policies that are beginning to move the energy system in that direction. Some US states and some countries in other regions are doing the same. China is investing massively in renewable energy capacity, though it is simultaneously continuing to invest in coal. Some corporations are beginning to genuinely decarbonize their operations, though many are also engaged in greenwashing that is more appearance than substance. The transition is beginning. It is just not happening anywhere near fast enough to avoid significant warming. And this is where the Moscow snowfall connects back to everything else, because that snowfall was not just a meteorological event. It was a signal of a system in transition. It is what you get when you push a planetary system past its stability threshold. The records are falling because the system is reorganizing. The blocking patterns are forming because the jet stream is destabilizing. The ocean is heating because we have trapped more heat in the atmosphere. All of it is connected. All of it is expression of the same underlying physics applied to a system that has been pushed far outside its historical range. The people who recorded the snowfall in Moscow in 1880 were documenting a world that was, in some sense, more stable and more predictable than the one we live in now. There is a certain irony in the fact that their record stood for a century and 4 decades, seemingly invincible, seemingly a marker of the extreme conditions that the climate could produce, and then it fell. Not because the climate returned to the conditions that produced it, but because the climate has moved to a new regime where the records of the past are becoming ordinary, and the truly extreme events are becoming unprecedented. The future state of the climate depends on choices we make now. How rapidly do we transition away from fossil fuels? How much do we invest in adaptation infrastructure for the regions that will be disrupted? How do we manage the transition in a way that does not abandon the parts of the world that are least responsible for the emissions and most vulnerable to the consequences? How do we maintain social and political stability in the face of the disruptions that are already beginning? How do we prevent the climate change from becoming a source of geopolitical conflict, as regions compete for resources and climate refugees seek to relocate? These are not questions that have scientific answers. These are questions that have political answers and economic answers and ethical answers. Scientists can tell you what the physical consequences of different levels of warming will be. Scientists can model what will happen if we transition to renewable energy. Scientists can project what will happen if we do nothing. But scientists cannot tell you what you should do. That is a question that each society has to answer for itself, through institutions and processes that are designed to balance competing interests and values. What we can say, with high confidence, is that doing nothing is not an option. Inaction is a choice, and it is a choice with consequences that we can already begin to see. The feedback loops are activating, the records are falling, the system is accelerating toward a new state. If we do nothing, we will arrive at that new state passively, having failed to guide the transition in any deliberate direction. We will get whatever comes, and it is likely to be more severe and more chaotic than the outcomes we could achieve through deliberate policy. If we act, if we begin the transition now and commit resources to it and prioritize it, we can make a difference. We cannot avoid warming, the inertia is too large. But we can influence how much warming we get and how severe the consequences are. We can invest in adaptation infrastructure to help regions that will be disrupted. We can create managed transitions for communities that depend on fossil fuels so that they are not simply abandoned. We can build institutions that are designed to handle the disruptions that are coming and the uncertainties that will accompany them. This is not a story about planetary disaster that is already determined. This is a story about a planetary system that has been pushed out of its stable state and is now moving into a new regime, and human choices about how rapidly and deliberately we guide that transition will determine the character of the outcome we live with. The blocking patterns will keep forming. The Arctic will keep warming. The records will keep falling. These are not things we can turn off, but the magnitude and the rate of change can be influenced. The consequences can be mitigated. The transition can be managed rather than merely endured. Moscow recorded a record snowfall a year ago. In a decade, in 2 decades, in half a century, if we stay on the current trajectory, that record might not seem like a record at all anymore. It might seem almost quaint. The truly extreme events will be something else, something we cannot yet quite imagine. Or, if we begin the transition now, and if we commit to it, and if we move fast enough, that record might stand for another century. Not because the climate has returned to stability, but because we have managed the transition in a way that allows human civilization to adapt and persist through it. The choice between those two futures has not been made yet. It is being made now. Every policy decision about energy infrastructure, every corporate decision about where to invest resources, every vote that is cast, every protest that is organized, every institution that is reformed or built, all of it is contributing to that choice. The choice is not in our hands in the sense that it is too late to stop climate change entirely. The choice is in our hands in the sense that we still have agency over how severe it becomes and how chaotic or managed the transition is. That is where we actually stand. Not at the edge of catastrophe that is about to unfold. We are in the middle of it. The catastrophe is here. It is arriving in record snowfalls and record heat waves and disrupted water cycles and shifting agricultural zones. It is arriving in the feedback loops that are beginning to activate, and the species that are beginning to disappear, and the communities that are beginning to migrate. But the magnitude of the catastrophe, the texture of the disruption, the character of the world we emerge into after this transition is complete, all of that is still not fully determined. It depends on what we choose to do now. That might sound like a heavy thing to sit with, and in some ways it is. But it is also the most honest assessment of where we stand. We cannot solve this by pretending it is not happening. We cannot solve this by waiting for a technological breakthrough that will let us have everything we have and not change anything. We cannot solve this by assuming that the market will handle it, or that someone else will solve it, or that it will work out. We are in the problem now. We are living through the transition. The only question left is whether we guide it consciously, or whether we let it happen to us. The meteorologists of 1880 could not have imagined what their records would eventually mean. They were simply doing their job, documenting the weather, maintaining archives. They had no way of knowing that 140 years later, their records would be a benchmark against which we would measure the speed of planetary change. They had no way of knowing that the simple act of recording a snowfall would contribute to humanity's understanding of how far we could push our own planet before it began to reorganize itself. We are the ones who know. We have the satellite data, we have the global sensor networks, we have the models and the understanding of the physics, we can see the feedback loops, we can measure the acceleration, we can project where this is going if we do not change course, and that knowledge comes with a responsibility. Not because we chose to push the planet to this point. That choice was made by previous generations, and we are living with the consequences, but because we are the generation that has the knowledge and the capability to choose a different path going forward. What we choose to do with that knowledge, what we choose to do with that capability, that is the actual story. Everything else is just context. The snow falling on Moscow, the heat rising in the oceans, the records breaking, the feedback loops activating, all of that is real and all of that matters. But it is not the whole story. The whole story includes us and the choices we make and the future we decide to build. and that story is not over yet. It is being written right now by institutions and individuals and societies all making decisions about what to prioritize, what to invest in, what kind of world to aim toward. That story does not have an ending yet. That is the part that depends on us. Continuation, part 1 of 2. Now, one thing I've been very careful not to say throughout this entire conversation is that the climate crisis is inevitable, or that human action cannot make a difference, or that we are locked into a predetermined future. That would not only be scientifically inaccurate, it would be a betrayal of what the data actually shows. Because the data shows something far more interesting than simple determinism. It shows a system with options. Think about what we have already accomplished without really trying. The Clean Air Act in the United States, passed in 1970, was not designed to address climate change. It was designed to address smog and acid rain and respiratory disease. But the sulfur reductions that came from cleaning up air pollution also reduced the inadvertent cooling effect I mentioned earlier, the dimming caused by sulfur aerosols. We did not intend to unmask warming. We were solving a different problem entirely. And yet the side effect of solving that problem was to make the climate change clearer and more accelerated. That is what I mean by the system having options. A single policy choice made for reasons entirely unrelated to climate shifted the entire trajectory of how we see and understand global warming. The reverse is also true. Policies designed to reduce carbon emissions also have side effects. When we transition to renewable energy, we improve air quality in cities. We reduce the particulate matter that harms human lungs. When we transition to renewable energy, we reduce the mining of coal and oil, which means we preserve ecosystems and prevent the destruction of landscapes and water systems. When we restructure agriculture to be less carbon intensive, we often improve soil health and reduce pesticide runoff. The climate problem and the environmental problem and the public health problem are not separate. They are the same problem viewed from different angles. Solving one means solving the others. This matters because it changes the political calculus around climate action. For a very long time, the conversation has been framed as though climate action requires sacrifice. It requires us to give up prosperity or comfort or energy abundance in order to save the planet. That is not an entirely false framing because there are real trade-offs and real costs to transitioning an energy system. But it is incomplete. It ignores the massive co-benefits that come from the transition. It ignores the fact that the air in Los Angeles is dramatically cleaner than it was in the 1970s, not because Californians wanted to sacrifice, but because they wanted to breathe without coughing. The climate benefits came along as a bonus. The same could be true at a global scale if we restructured the conversation around the benefits rather than the costs. Renewable energy is increasingly cheaper than fossil fuel energy. Battery technology is getting better every year. Solar panels have dropped in price by 90% in the past decade. There is no reason that the energy transition should make people poorer. There are reasons why it disrupts existing industries and existing power structures, and those are legitimate reasons for resistance. But if we can create new jobs faster than we eliminate old ones, if we can make the transition economically positive for most people, then the resistance becomes a question of political will rather than economic reality. But there is another layer to this that does not get discussed enough, and it is the question of what the alternative actually costs. Because the cost of climate action is real, but the cost of inaction is also real, and increasingly it is measurable. The wildfires that have become routine in the American West and in Australia and in the Mediterranean cost hundreds of billions of dollars in damages and suppression efforts. The floods that are becoming more intense in many regions because of changes in precipitation patterns cost massive amounts in repairs and insurance payouts. The droughts that are disrupting agricultural production cost money in failed crops and food price spikes. The heat waves that are killing people and disrupting infrastructure cost lives and resources. Climate action is not a choice between spending money and not spending money. It is a choice between spending money on the transition now or spending vastly more money on adaptation and disaster response and economic disruption later. And that is before you even get to the non-economic costs, the suffering and the human displacement and the species extinctions and the social destabilization that comes from rapid, unmanaged climate change. This is where the conversation becomes genuinely difficult for policymakers, because it requires comparing two things that are hard to compare. The costs of action are concentrated and visible and immediate. The costs of inaction are diffuse and future, and distributed around the world in ways that are hard to attribute directly to climate change. A politician who votes for a renewable energy policy has to face voters whose energy bills might increase. A politician who does nothing about climate change will not face voters in 50 years whose communities have been disrupted by climate change, because those voters either will not exist or will be in different countries. The political incentives are not aligned with the long-term consequences. This is not a problem that science can solve. This is a problem that governance has to solve. And governance is slow. It is designed to be slow, because moving slowly means that you have time to accommodate different interests and build consensus. But climate change is fast. The feedback loops are activating, the records are falling, the system is accelerating, and institutions that move slowly are by definition going to fall behind a system that is accelerating. That is not a judgment on the institutions. It is just a statement of fact about time and change. There have been periods in human history when institutions adapted quickly to new circumstances. The mobilization for World War II is often cited as an example. Entire economies were restructured within months. Factories that had been producing consumer goods were converted to military production. Labour markets shifted dramatically. Supply chains were reorganized. It was not comfortable. It was not equitable. But it happened remarkably fast by the standards of institutional change. The question facing us now is whether we can mobilize at a comparable speed, not for war but for survival. And so far the answer has been no. We are not mobilizing fast enough. But this is also where individual action becomes important, not as a substitute for systemic change, but as a precursor to it. The fossil fuel industry has spent decades trying to convince people that climate change is an individual responsibility problem, that if only everyone would change their personal consumption habits, the problem would be solved. That is in many ways a distraction and a deflection. The vast majority of carbon emissions come from a relatively small number of sources. Individual lifestyle changes cannot solve the problem. Structural changes to energy systems and industrial processes are necessary, and yet individual changes matter for a different reason. They matter because they are how social movements grow. They matter because they are how people signal to each other that the old normal is no longer acceptable. They matter because they are how communities organize around a shared understanding that change is necessary. When enough people understand that the climate is in crisis and that we need to do something about it, those people become a political force. They elect officials who will implement the policies needed. They invest in companies and technologies that are aligned with climate action. They withdraw investment from companies that are not. They apply pressure. This is how social change happens. It starts with a shift in consciousness, moves to individual action, scales to community organizing, and eventually reaches the level of systemic policy change. We are somewhere in the middle of that process now. The consciousness is growing. The individual actions are happening. Community organizing is occurring in pockets around the world. The systemic policy changes are coming slowly and unevenly, but they are coming. The question is whether they are coming fast enough. Here is a specific example that illustrates what is possible. The cost of solar electricity has dropped from multiple dollars per kilowatt hour in the 80s to a few cents per kilowatt hour today. That drop was not because some genius invented a new physics of solar panels. It was because we collectively decided to invest in solar as a technology. We subsidized it when it was expensive. We created policies that incentivized its development. We removed regulatory barriers to its deployment. We invested in manufacturing capacity that allowed economies of scale. The result is that solar is now cheaper than fossil fuels in most parts of the world. That is not a small thing. That is a reversal of the entire economic logic that has supported fossil fuels for 200 years. The same thing is happening with batteries. Battery technology has improved dramatically because we invested in it. The cost of lithium-ion batteries has dropped by 90% in the past 15 years. Electric vehicles are becoming competitive with gasoline vehicles. As battery costs continue to drop, which all indicators suggest they will, the economics of transportation will shift entirely. A person choosing an electric car will not be making a sacrifice for the environment. They will be making an economically rational choice to buy a cheaper, cleaner vehicle. This is not happening everywhere at the same speed, and there are still massive barriers to overcome. The electricity grid needs to be redesigned to handle distributed generation from solar and wind. Energy storage needs to scale up dramatically. Supply chains for batteries and solar panels and wind turbines need to be organised. Industrial processes that currently rely on fossil fuels for heat need to be converted to electric heating. Heavy transportation and aviation, which are particularly difficult to decarbonise, need technological solutions that do not yet exist at scale. But none of these are impossible. They're all engineering problems with engineering solutions. They just require resources and coordination and political will. And this is where I want to shift the conversation slightly, because there is a part of the climate change narrative that often gets left out, and it is the part about what we are actually fighting for. We tend to talk about climate change in negative terms. We talk about what we are trying to prevent, what we are trying to avoid. We talk about limiting warming to 1.5 degrees or 2 degrees. We talk about preventing the catastrophic scenarios. We talk about not letting the planet become uninhabitable. These are all true and important, but they are all framed around prevention and avoidance. But there is another way to think about it, which is to ask what kind of world we actually want to live in. What does a decarbonised world look like? What does a world powered by renewable energy look like? What does agriculture look like when it's no longer burning fossil fuels to pump water and produce fertiliser and run machinery? What does transportation look like when it is no longer dependent on burning gasoline? What does manufacturing look like when it is powered by renewable electricity? The answers to those questions are not obvious, because we have not really built those systems at scale. But there are glimpses. There are places that are further along in the transition. Denmark generates about 80% of its electricity from wind. The electricity grid in Denmark is stable and reliable, and cheaper than many other European countries. Costa Rica regularly generates more than 90% of its electricity from renewables. Iceland heats nearly all its buildings with geothermal energy. These are not small, unlivable societies. They are wealthy, developed countries with high standards of living that have already largely decarbonised their energy systems. If we go further and we imagine a truly decarbonised world, what emerges is interesting. Cities would be quieter, because most of the noise pollution comes from vehicles burning fuel. The air would be cleaner. The water systems would be less contaminated, because we would not be pumping petroleum products into the ground and the air. The countryside would be less disrupted, because we would not need to extract coal or drill for oil. There would be more space for natural ecosystems to recover. The agriculture would be less dependent on industrial chemistry, and more aligned with regenerating soil health. There would be less political conflict over access to oil resources. None of this is to say that a decarbonised world would be perfect or free of problems. It would have different problems. Energy systems still sometimes fail. Renewable energy can be disrupted by extreme weather. Manufacturing and agriculture still require resources and create waste. But the problems would be different from the problems we have now, and many of them would be smaller. This is the vision that is missing from a lot of climate communication. We talk about what we are preventing. We do not talk enough about what we are building toward. And that matters psychologically and politically. People are willing to endure disruption and change and sacrifice if they understand that the change is leading somewhere worth going. They are much less willing if they think they are just making sacrifices for some abstract goal. So part of the work of communicating about climate change is not just explaining the problem, it is articulating the vision of the solution. But there is a complication, and this is where the conversation becomes genuinely complex. The decarbonised world that would be more livable in many ways would also require some people to live differently than they do now. The person who drives 50 miles to work every day would not be able to do that in a way powered entirely by renewable energy, because renewable energy requires planning and load management. They would have to move closer to work or work remotely or use public transportation. The person who flies across the country multiple times per year would have to fly less often, because aviation powered entirely by renewable electricity is not technically feasible at current levels of demand. The person who has built their life around suburban sprawl and automobile dependence would have to rebuild their life around a different pattern. These are not small changes, they involve real disruptions to how people live. And for people who have been privileged by the current system, the prospect of living differently is not appealing. This is where a lot of the political resistance to climate action actually comes from. It is not that people do not believe climate change is happening. It is that the prospect of changing their own lives is uncomfortable, and they are looking for reasons to believe that change is not necessary or not possible. But here is the thing that often does not get articulated clearly. The change is happening anyway. Whether we manage it and direct it intentionally, or whether we let it happen passively, the climate is changing. The agricultural zones are shifting. The water patterns are disrupting. The regions that have been habitable are becoming harder to live in, while other regions are becoming more habitable. People are going to have to relocate. People are going to have to change how they live. The only question is whether that change happens in an intentional, coordinated, managed way, or whether it happens chaotically, driven by disaster and crisis. A managed transition is uncomfortable. It requires some people to move, some industries to transform, some infrastructure to be rebuilt. But it is far less uncomfortable than a chaotic transition. A chaotic transition involves failed crops and food shortages. It involves water scarcity and conflicts over water. It involves large-scale migration and refugee crises. It involves disrupted supply chains and economic collapse. It involves suffering on a scale that is hard to really imagine until you are living through it. So the actual choice is not between changing and staying the same. The actual choice is between managing the change and enduring the chaos of unmanaged change. And when you frame it that way, suddenly the case for climate action becomes far stronger than when you frame it as a sacrifice. This is where we actually find ourselves right now. The choice has not been between action and inaction. That choice is over. The climate has already changed. We have already locked in significant warming. We are already experiencing the consequences. The choice we have now is between management and chaos. We can try to guide the transition in a direction that minimizes suffering and preserves the things we value. Or we can let it happen to us and deal with whatever emerges. And this brings us back to the Moscow snowfall, because that snowfall is part of the transition we are in. It is not a separate event. It is not an anomaly that should make us question whether warming is happening. It is exactly what you get when you push a planetary system out of its stable state. You get unusual weather in unusual places. You get records falling. You get the system reorganizing itself. The Moscow snowfall is telling us that we are in the transition. It is telling us that the old normal is gone. It is telling us that we need to think about how we want to navigate the new normal that is arriving. The question is whether we are paying attention to that message. Are we hearing it? Are we understanding that it is not just a weather event but a signal? Are we beginning to organize our institutions and our investments and our policies around the understanding that the transition is here and we need to guide it rather than resist it? The answers so far are mixed. Some places are moving quickly toward decarbonization. Some places are moving slowly. Some places are actively resisting. Some people understand the urgency and are pushing for change. Some people are in denial or are benefiting from the status quo and are actively fighting change. The global response is not coordinated. It is fragmented and uneven, and that fragmentation is one of the biggest risks, because it means that we are not mobilizing at the scale and speed that the problem requires. The physics does not negotiate. The feedback loops do not care about political disagreements. The records will keep falling whether we are ready or not. The system will keep accelerating whether we have a plan or not. So the next question, the one we have to sit with now, is whether we are going to get serious about this, or whether we're going to keep treating it as something that will be solved by someone else in some other place at some other time. Continuation, part 2 of 2, because that is the actual dynamic that is keeping us from acting at the scale needed. We keep thinking that someone else will handle it. The government will solve it. The scientist will come up with a breakthrough. The free market will fix it. The next generation will deal with it. And as long as we are thinking that way, as long as we are assuming that this is someone else's problem, we are not going to do the things that actually need to be done. But the things that need to be done are not actually mysterious. They are clear. They are well understood by people who have spent careers studying the problem. Decarbonize the electricity system, transition to electric transportation, electrify heating, improve industrial processes to be less energy intensive, transition agriculture to be regenerative rather than extractive, protect and restore natural ecosystems because they are carbon sinks and they are buffers against climate disruption, create institutions and governance structures that can manage the transition in a way that is equitable and does not leave behind the people who are most vulnerable to climate change. All of these things are doable. None of them require waiting for some future technology. They all exist now. They just require resources and coordination and political will. The resources exist. There is enough capital in the world to fund the energy transition multiple times over. The coordination is the hard part. Getting different countries and different industries and different communities to all move in the same direction is genuinely difficult, especially when there are powerful interests benefiting from the status quo. But coordination is not impossible. We coordinate on other things all the time. We coordinate global supply chains that are astoundingly complex. We coordinate on internet protocols that connect billions of devices. We coordinate on aviation safety and maritime law and intellectual property. When we decide that something is important enough, we figure out how to coordinate. Climate change needs to be treated like a problem that is important enough to coordinate on, and that means governments actually implementing policies that are going to be disruptive to existing interests. It means corporations actually investing in transitions that cannibalize their existing business models. It means individuals actually changing consumption patterns. It means communities actually building new institutions designed for a world different from the one we have now. There is one more piece of this conversation that deserves attention, and it is the question of justice. Because climate change is not affecting everyone equally. It is not hitting hard equally everywhere. The places that have benefited most from the fossil fuel economy, the wealthy nations of North America and Europe and East Asia, are generally weathering climate change better than the places that have benefited least. A farmer in sub-Saharan Africa is being hit much harder by changing rainfall patterns than a farmer in Denmark with irrigation and capital and insurance. A small island nation in the Pacific is being hit much harder by sea level rise than a landlocked country. A person in poverty is being hit harder by heat waves and floods and economic disruption than a wealthy person who can afford air conditioning and can relocate if necessary. The people least responsible for causing climate change are bearing the worst consequences. That is not a small ethical problem. It is a massive one. It is the kind of injustice that has historically been a source of conflict. And if we try to manage the climate transition without addressing this fundamental inequity, we're going to create exactly the kind of conditions for conflict and suffering and destabilization that we are trying to avoid. This is why climate action cannot be separated from development justice and economic equity. We cannot ask poor countries to sacrifice development in order to prevent warming caused by rich countries burning fossil fuels to get rich. That is not sustainable politically or ethically. We have to find pathways for poor countries to develop in ways that are not dependent on burning coal and oil. We have to transfer capital and technology to make that possible. We have to accept that the wealthy countries bear a disproportionate responsibility for funding the transition. This is not charity. This is enlightened self-interest. The climate crisis is not going to be solved unless all the major emitters are moving in the same direction, and you cannot get all the major emitters moving in the same direction unless you address the inequity that would otherwise cause them to resist and to pursue their own interests at the expense of the common good. So the real project of climate action, the thing that has to happen for this to work at all, is threefold. It is decarbonising the energy system. It is building institutions and governance structures that can manage the transition. And it is creating a pathway for global equity so that we can do those first two things in a way that does not create backlash and resistance from the parts of the world that have been left behind. None of this is simple. All of it is difficult, but difficult is not the same as impossible. And the timeline we are working with is not infinitely long. We have roughly 1 decade, maybe a bit more, to get the global emissions trajectory to start declining. After that, the warming becomes increasingly locked in, and the consequences become increasingly severe. 1 decade is not long. It is not enough time to accomplish all of these things if we are moving at current speeds. But it is enough time if we actually accelerate and if we actually commit resources, and if we actually decide that this is worth organising ourselves around. So what does it look like if we make that decision? What does it look like if we actually mobilise at scale? It looks like rapidly scaling renewable energy deployment. Solar and wind installations increasing not by percent but by multiples. Battery manufacturing ramping up to provide energy storage. Grid infrastructure being rebuilt to handle distributed generation. All of this requires investment, but the investment is already starting to happen. The cost of capital for renewable energy projects is lower than it used to be, because investors are confident that the returns will materialise. The question is whether the investment scales fast enough. It looks like electrifying transportation. Electric vehicles becoming the default rather than the exception, not in wealthy countries alone, but everywhere. That requires manufacturing capacity in multiple regions, not just a few. It requires building out charging infrastructure. It requires the energy system to be able to support the load. It requires policy supporting the transition. All of these are happening piecemeal in various places. The question is whether they happen globally and whether they happen fast enough. It looks like transforming how we produce heat. In many parts of the world, fossil fuels are burned to heat buildings and to provide industrial heat for manufacturing. Replacing that with electric heat pumps powered by renewable electricity is technically straightforward, but requires massive infrastructure investment. It requires retrofitting buildings. It requires manufacturing the equipment. It requires policy supporting the transition. It is doable, but only at significant scale. It looks like transforming agriculture. Industrial agriculture is dependent on fossil fuels. We use them to make fertilizer. We use them to pump water. We use them to run machinery. We use them to transport food. Transitioning to regenerative agriculture that builds soil health and reduces inputs is possible, and in many cases more productive long-term. But it requires a different approach to farming that takes longer to learn and is riskier in the short term. Supporting farmers through that transition requires policy and capital. It looks like actually protecting and restoring natural ecosystems at scale. Forests are carbon sinks. Wetlands are carbon sinks. Grasslands manage carbon in their soils. All of these can be protected or restored, and that protection and restoration acts as a buffer against climate disruption and also sequesters carbon. But it requires deciding that those ecosystems have value beyond their extractive economic value. It requires policy and coordination. It looks like building institutions of global coordination that can manage this transition equitably. That might sound abstract, but it is actually quite concrete. It means international agreements that actually commit countries to specific emission reduction targets. It means mechanisms for transfer of capital and technology to poorer countries. It means trade rules that are designed to support the transition rather than undermine it. It means labour agreements that protect workers displaced by the transition. It means governance structures that can move faster than traditional international institutions. All of this together, all of this at global scale, happening in the next decade. That is what it looks like if we actually mobilize. And yes, it is ambitious. Yes, it is difficult. But so was building the global infrastructure we have now. The energy system we currently have was built deliberately, over time, with massive investment and policy support. We can build a different system in the same way. It will not be easy. It will be disruptive. It will require sacrifices, but it is possible. And here is the thing that I think is most important to understand about the moment we are in. We do not have to guess whether this is possible. We have examples. Denmark has restructured its energy system. Germany has deployed solar and wind at massive scale. The United States has passed legislation that is actually directing hundreds of billions of dollars toward clean energy infrastructure. China is manufacturing batteries and solar panels faster than any other country. Electric vehicles are being adopted at accelerating rates in multiple countries. Some agricultural regions are transitioning to regenerative practices and showing that it can work. Some communities are restructuring in ways that are less dependent on cars and fossil fuels. These are not hypothetical possibilities. These are things that are actually happening now. The question is not whether it is possible. The question is whether we are going to do it fast enough and at global scale. And here is where the individual and the systemic finally connect, because the speed at which this happens depends on both. It depends on policies and investments and coordination. But it also depends on social movement and pressure, and the willingness of people to believe that change is necessary and to push for it. When enough people understand that the transition is coming, and that we have agency in determining the character of that transition, when enough people decide that the status quo is no longer acceptable, then the institutions begin to move faster. It is not one or the other. It is both at once. This is why the conversation matters. This is why paying attention to the science matters. This is why understanding that the Moscow snowfall is not an isolated event, but a signal matters. Because understanding that drives behavior. Understanding that people understand that we are in the transition and that we have choices about how to manage it. And those choices, aggregated across billions of people and thousands of institutions, determine the future. So what does that mean for you, the person listening to this, who presumably cares enough about the topic to hear me out for 2 hours? What is the actual work that you are being asked to do? The first part is to understand the problem, to actually get the physics of it, to understand that it is not just warming, but acceleration and feedback loops and systemic disruption. To understand that it is not someone else's problem in some far-off future. It is here now. That understanding has to be genuine. not intellectually acknowledged but then forgotten, genuinely held. The second part is to live according to that understanding. That does not mean you have to go live off the grid and deny yourself everything. It means making choices that are aligned with the understanding that the transition is necessary. That might mean driving an electric car or using public transportation if you can. That might mean reducing flights if you travel a lot. That might mean supporting renewable energy if you have a choice in how your electricity is generated. That might mean eating less meat or being conscious about where your food comes from. That might mean supporting companies and investments that are aligned with the transition and withdrawing support from ones that are not. Small choices that signal that you understand the trajectory and you are choosing to move with it rather than against it. The third part is to be willing to have conversations about this with people who do not understand it yet, to not be preachy or self-righteous, because that does not work, but to be willing to explain it, to share the information, to help people understand why this matters. Because the transition does not happen without social movement, and social movement starts with people talking to other people. The fourth part is to support and vote for policies and politicians who are actually taking the climate crisis seriously. Not just paying lip service to it, but actually implementing the changes that need to happen. That might mean voting for a politician you do not particularly like because they have better climate policy. That might mean supporting ballot measures that fund renewable energy, or public transportation, or climate adaptation. That might mean joining or donating to organisations that are pushing for change. The fifth part is to invest, if you are in a position to do so, in companies and technologies that are aligned with the transition. That might mean putting your savings in funds that exclude fossil fuels. That might mean actually investing in renewable energy companies or clean technology startups. That might mean directing capital toward businesses that are leading the transition rather than resisting it. Capital follows opportunity. If capital goes toward the transition accelerates. The sixth part is to be willing to challenge power and to be willing to be part of pressure for systemic change. Because the transition will not happen at the speed needed unless we push, unless we challenge the fossil fuel interests that are resisting change, unless we demand that governments move faster, unless we are willing to be inconvenient and to make it more expensive to maintain the status quo than to change. And the seventh part, the part that is hardest to articulate but maybe most important, is to hold on to the vision of what we are building toward. Not just what we are preventing, but what we are creating. A world that is more livable in many ways than the one we have now. A world with cleaner air and cleaner water. A world that is not dependent on the extraction and destruction that has characterized the age of fossil fuels. A world where energy is local and distributed. A world where we have more control over our own fates, and we are less dependent on distant supply chains and global power structures. That vision is what makes the sacrifice meaningful. That vision is what keeps people moving even when the work is hard. Because the work is going to be hard. The transition is going to be disruptive and uncomfortable in ways that we cannot fully predict. There are going to be failures and missteps, and directions that we try and find are not viable. There are going to be times when it seems like the problem is too large and the resistance is too great and progress is impossible. But we have done hard things before as a species. We have solved difficult coordination problems. We have built complex systems. We have transformed our relationship to nature and to each other. This is not fundamentally different. It is just different in specific ways. And here is what is important to understand about where we are right now. The hardest part of the transition is not the technology. The technology exists. It is not the resources. The resources exist. The hardest part is the collective decision to do it. The hardest part is overcoming inertia and resistance and the sunk interests in the old system. But that is something that we as a society can actually change. That is something that is within our control in ways that the laws of physics are not. The feedback loops will keep accelerating. The Arctic will keep warming. The records will keep falling. That is locked in. But the response to those changes, the way we organize ourselves in the face of them, that is not locked in. That is still being written. That is still being decided by the choices that we make and the institutions that we build and the priorities that we set. Moscow will see snow. It might not set a record next year or the year after or the year after that. It might not set another record for decades. Or if the blocking patterns continue to form as the Arctic warms further, it might set new records. We do not know. The system is entering new territory that we have not seen before. But what we do know is that the future state of the climate is not predetermined. It is being determined right now by choices we are making or failing to make. So the final thing I want to say, the thing that I want to leave you with, is this. The planet crossed a line that was set in 1880. A record fell. A measurement that had stood for 140 years became obsolete in a matter of hours. That is a real signal. That is a real message that something has changed fundamentally about the stability of the system we live on, but the planet is going to keep changing regardless. The question is what we do with that fact. Do we treat it as a problem to be solved by someone else? Or do we treat it as a call to action? Do we treat it as something that has already happened and nothing can be done? Or do we treat it as an opening to build something different? Because that is where we actually are. We're not in a story about inevitable decline or predetermined catastrophe. We are in a story about a planetary transition and the human choices that will determine the character of that transition. We are in a story that is still being written. We are in a story that does not have an ending yet. That is not false hope. That is the accurate assessment of where we stand. The physics is real. The feedback loops are real. The disruption is coming. All of that is true. But what we do in response to it, the choices we make, the institutions we build, the priorities we set, all of that is still open. All of that is still being determined by what we choose to do. The snowfall in Moscow was a message from a planetary system in transition, a message that the old normal is gone and something new is arriving, and we are the ones who get to decide what that new thing is. That is the actual story, not the past 140 years and the record that fell. The actual story is now. It is us. It is what we choose to do with the knowledge that we have and the agency that we still possess.